In our lesson for 6.4a, we are going to take this application of exponential functions in real life situations and use it in a way that is really common, which is describing exponential growth in terms of a percentage. So there's a couple of things we're going to talk about today, and one of those is taking this equation we've been playing around with for a while, the kind of general exponential equation, and then understanding that that multiplier can be represented instead as 1 plus a growth factor that is usually given as a percentage. So a is still going to be our initial quantity, x is still going to be in our exponent, but the way that we describe our rate of increase is going to be, or that multiplying base here, is going to be 1 plus r, which in our case is usually a percent increase. And a lot of times that's what you hear when you're hearing conversations about, oh, you know, like Travis area is growing so quickly, it's growing exponentially, or they might say our districts has grown 11% every year over the last 5 years. That's a really common way to describe growth. And when you hear growth being described in terms of a percentage, it's exponential. And it looks like this. And so that's what we're going to modify what we've been working with this kind of application. This, as well as we're also going to talk about another really common application for exponential increase, which is compounded interest. You've already talked about simple interest, and I believe compounded interest when it was compounded only annually, but we're going to take it a step further and really explore some of the other setups that sometimes financial institutions, banks, loans, things like that have, where they compound semi-annually, quarterly, and more than just once a year. So we're going to work with that as well. So let's get started. So first of all, a function of this form, where a is strictly positive now, and r is positive, is an exponential growth function. So let's write that down. This is exponential growth function. And you can see a lot of the ingredients are still the same, except, you know, our output is our final resulting, you know, amount. We have a as our initial amount, and then our base becomes 1 plus whatever the rate of growth is in decimal form. So always remember that right here, we're going to take our percentages and change them to decimals before we use them. Okay, that's a biggie. And then we insert that here. And then our exponent really becomes what is happening over time. Okay, now together this b is still your growth factor. So this is a common misconception here, the difference between the rate of growth, or your growth rate, and your growth factor. A growth factor is something you multiply by. It's your final base here. It's whatever 1 plus that decimal is together. That's your growth factor. The rate of growth is that r decimal, or that r value that you added to the one. So they sound similar, but they're actually two different things, so just be careful with that. So let's just put this into context and do a couple of practice problems. Let's start with number 1. The first thing we want to do is identify the growth factor in the scenario, and then we're going to rewrite it as an exponential growth function that represents the situation, right? So in number 1, if it tells you the foundation of your house has about 1,200 termites, yikes. The termite population is growing at a rate of about 2.4% per day. Okay, so first let's come up with the growth factor. So our growth factor here is that 1 plus r. So for us, it is going to be 1 plus r, where r is our percent, or a rate of growth. It's this percentage. So we'll change that to a decimal, right? So we know that 2.4% is really 0.024. And so this is now going to become for us 1 plus that decimal. Oh, that's a 4. Just kidding. And so our growth factor what our new multiplier here, our b, is going to be 1 plus that percentage as a decimal. So for us, it is 1.024. That is our growth factor right there. Okay. Then we're going to define our variables. Okay, so now that we know that this is our growth factor, let's lay out what we know. The initial quantity of termites in the house is 1,200 right now, where they found them. And then our R value is that 2.4%, or if you write it as a decimal, it's that 0.024. And then T represents time in days, because it's per day here. Time in days. Okay. And that allows us to then write an exponential growth function. So when we go to write our exponential growth function, we just need to fill in our A value, our growth factor, and use T as our exponent. So for our function over here, our function would be y equals our initial quantity. We started off with 1,200 termites. This is the rate that they are growing at, plus 1 gives us our growth factor, and that's raised to the t power. Okay, so we're just inserting that initial. Notice this is greater than 1, so that's consistent with this growing. This would have been our b value a couple of days ago, but now it's a little bit more specific and more informative. That b value really represents the rate of growth, and when we add the 1 to it and use it in our function, it'll always give us an output that is our total quantity amount, not just how much it increased, but what our final amount is. Okay, all right, let's try it again. Let's do another one here. We've got, in 1985, there were 285 cell phone subscribers in Bastrop. The number of subscribers increased by 75% per year after 1985. So if we go through this again, we're going to find, number 1, find your growth factor. To do that, it's 1 plus R. And in this particular problem, R is at 75%. So I make sure that I change that to a decimal before I add it to 1. And that sum is going to give us, 1.75. There you go. So 1.75 is our growth factor. Okay, so there it is. That's going to be our growth factor that we're going to multiply our initial quantity by. Let's define our variables. So in this case, A is going to be our initial quantity. It looks like in 1985 we started with 285 cell phone subscribers in Bastrop. Our R, or our rate of increase here, is 75%, or if we use that as a decimal, 0.75. And T is going to represent the number of years after 1985. This is important. A lot of the problems will do this. And it's important because that means that we're not going to put it in 1985. Like if I was looking at 1985 as my year, I wouldn't be using 1985 as my input. I would be using 0 because that's my starting amount. It's, year. This is how many years after 1985. So like if I wanted to know the number of cell phone users in 1988, I wouldn't want to put a 1988 in there. I would want to think, oh, okay, well, 1988 is 3 years after 1985, so I would use 3 as my exponent, right? I would find the difference there and say, oh, it's been 3 years. That's going to be the exponent I'm going to use. So just be careful with that. That comes up quite a bit. We have defined those. Again, we can then write our final function. So for our function, we're just going to fill in the blanks. Our output, or our final amount, is going to be this initial quantity times our growth factor to the t, where t is the number of years after 1985. Okay, so I would say put a pause on this, try the next two, and then you can check your work and see how that went. Find the growth factor, define your variables, and then write the function. Okay, so go ahead and check your answers here on numbers 3 and 4. So on number 3, the deer population in Lakeway increases at a rate of 2% per year. there are 1,573 deer in Lakeway this year. So first, for our growth factor, once again, 1 plus the growth rate. We change that to a decimal, we add it, we get 1.02. Then we define our variables. A is going to be our initial population, 1,573. R is, of course, our percent increase. And T is how many years after they're gathering the data. This is starting point is this year. So T is going to then represent how many years after this year, which is still 2019, have passed. And so this would be our function. And then for number 4, the amount of money spent at the Bee Cave Galleria increased 12% each year since it opened. So the first year it opened, it made $14 million. It was, were spent. So again, that 12% becomes a decimal. We add it to 1. That gives us our growth rate. A is going to be 14. We're going to do it in millions. You could put 0, 0, 0, 0, 0 after that, but we could just call it 14 and just make a note that whatever input outputs we have here, they're going to be in the millions. Makes our life a little bit easier. And then our, of course, rate of growth is 12%, and then T is how many years since it has opened. So this would be our function. There's our Y equals A initial value times growth factor to the T power. Okay, so hopefully you're feeling comfortable taking information that is based on a percent increase and creating the exponential function based on that. Let's go ahead and actually start solving or evaluating some of this stuff now that we know how to set it up. So now we're actually going to use the functions that we create for something, to find some meaningful information, if you will. So take a look at number 5. On number 5, we're talking about the population of Winnemucca, Nevada. Wow, why did we pick that? I don't know. That was hard to say. So the population of Winnemucca, Nevada can be modeled by this function right here, where T is the number of years since 1990. So keep that in mind. I mentioned that on the front page, right? So T, we're going to have to do a little math. We're not going to just stick a year value here. We're going to find how many years have passed since 1990. Okay, so by what percent did the population increase? So we're kind of working backwards here, right? They gave us, we can see that growth factor, but we want to be able to extract from that what was the population increase as a percent. So that's what we're looking for here. And if we kind of break this down a little bit, this is our initial population because that's our A. So let's write that down. So initial population. Okay, it's going to be that 6,191. But then this growth rate, this growth factor, see there I go, okay, is really 1 plus R. Okay, so now what I want to know in part A here is what is R. So if I just kind of set that up and think about the decimal part here that was added to the 1, I can see that R was that 0.04 that I see after the 1 there, which means 4%, right? So if I get 0.04, which is the part that was added to 1 here, that means that it is 4%. So that allows me to answer this question over here. The population increases by 4% each year. Okay, so let's write that down. The population increases 4% each year. Okay, and so all we did was take the growth factor and rewrite it as 1 plus R and solve for R to get the growth rate. Okay, so there is 4% each year. And then it wants to know what was the population in 1990. Well, that's our initial quantity, which since this was based on 1990, that would have been our starting amount, which we can always find right there as that A value. So if we know where to look, this is a very easy question because it's already, the answer is in the equation already for us. So then we can answer this and say the initial population in 1990 was that 6,191 people. And there it is. Okay, so that's really just reading the problem instead of kind of and then creating the function. In this problem, we practiced having the function and being able to extract the information that we want to know about from the function itself. So there you go. There's that one. Okay, let's go on to number 6. It says in 1971, there were 294. Wow, good morning. So 294,105 females participating in high school sports. Since then, that number has increased by 14% every year. So part A here, we want to write an equation to represent the number of females participating in high school sports T years since 1971. So that's what T is going to represent there. So let's do that first. So let's break down what ingredients I need for my function. I need an initial value. I need an R, and I need to define what T is going to represent. So here our initial looks like there was that 294,105. The rate is 14%, which we're going to change to a decimal so that we can add it to the 1 in a moment. T is going to represent the number of years since 1971. Okay, so if I write this function, it's going to be y equals a parentheses 1 plus r to the t, and then we'll modify that to our situation. Our initial is 294,105, and then 1 plus that decimal is just 1.14. And then to the t power, where t is the number of years since 1971. So that would be our function right there, okay, for part A. How many females would participate today if this trend continued? So we have a function that can help us make that prediction. We just have to be careful about what we're going to put in here. So today we're in the year 2019, right? We're in the year 2019. We're not going to put a 2019 there. We need to find out how many years have passed since 1971. So for us to do this, we got to take this year and subtract 1971 from it, find out how many years have taken place, right? So for us, that's going to be a 19, that's going to be a 48 years. Okay, so we're looking at 48 years have passed. That's going to be our t value that we're going to plug in if we want to have an accurate number here. So we're going to take our function and solve it for an exponent of 48. Okay, and then we're most definitely going to grab a calculator for this. Nobody's expecting to do this in your head at all. So we'll grab our calculator and we're going to just enter our initial amount times our growth factor raised to the amount of time we're interested in. Quite a bit, right? We've come a long way, ladies. All right, so this is our, and I'll just bump that up to 700 there because it's already 0.5 and we're not going to have half of an athlete anyway. So we're looking at about 1.5. Let's write it down first and then I'll figure out how to read it. Okay, so boom, boom. Yeah, so about 158,465,700 female athletes. Not bad. Okay, so that's our number there. So there will be about that many female athletes. There you go. Okay, so about 158,465,700 female athletes. So that's how you would evaluate it. We've practiced evaluating. We just hadn't done it for these that we've been writing. Okay. All right. Try number 7. Let's put a pause on this. Try number 7. Check it in just a moment. And if you feel good about it, we'll go on to compound interest. Okay. So check your work on these. In 2005, there were 100 rabbits in Polygon Park. The population increased 11% each year. So first we want to write an exponential growth function that represents the population t years after 2005. That would look like this. We started with 100 of them. They're increasing 11%, so we change that to a decimal, add 1. There's our function. We just want to remember that T is a number of years since 2005, not just a direct year input. So when they say, what will the population be in 2025, right? We don't want to just put a 2025 in here. That'd be kind of crazy. We really want to just find out, well, how many years have passed? If we're in 2025, how many years will it have been since 2005, which is 20 years? So that would be a T value of 20. That's what we plug in, and we evaluate that, and we round to the nearest whole number because we really hope there's no partial little bunnies going around. So about 806 rabbits, right? So there will be about 806 rabbits in 2025, approximately. I know that's kind of hard to see, but you can see it right there. Okay. So hopefully those went well for you, just working on those independently. And that's really one of the main applications, is really describing exponential growth in terms of a percentage increase. Really common. And then the other really common application then right here is our conversation around compound interest. So I know you've done a little bit with compound interest. We're just going to take it up a notch. So compound interest, write it down here. So compound interest is an interest earned on the principal as well as previously earned interest. That's the main distinguishing factor between that and simple interest. You're either paying or earning interest on not just the principal, not just your initial quantity, but also previously earned interest. The balance Y of an account is compounded interest looks like this. The reason this looks a little different is because we now have this N value here that basically represents how many times the interest is compounded per year. That's where this table is going to come in handy. Okay? So when you first did these back in 8th grade math, most likely you did annually compounded. So it was really just a P and then 1 plus R and then a T, and that was it. That's because you were only compounding once a year, which would mean that N would equal 1. And you probably guessed it. If you divide by 1, nothing happens. If you multiply by 1, nothing happens. So they probably didn't bother including the N. But the reality is that depending on the type of loan or savings or institution that you're working with, there's different ways you can compound interest. It's not just annually, but sometimes it is compounded semi-annually, which means twice a year. And now you have to take that into account both here and here. Okay, quarterly means 4 times a year. Monthly, you guessed it, 12 times per year. Daily would be approximately 365 times per year. Okay, so you're going to see how sometimes that affects how much either you owe or you've earned, depending on how they compound. But let's just practice a few of these so you can see this in motion. And I'm really, one of the most important things that I'm going to be doing here is modeling what I want this to look like in your work. Okay, so we want to write a function that represents the balance after T years. So right now we're going to just write a function for this. Okay, and then we're going to use it to solve. So if you have $3,000 and you deposit that, a $3,000 deposit that earns 4% annual, ding, 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 right, interest, but it's compounded quarterly, right? So there's some really key things here. First of all, that $3,000, that is our principal, our starting quantity. That is the P in the formula. If it earns 4%, that's your R value. Just don't forget to change it to a decimal. And then if it's compounded quarterly, well, that means 4 times a year. That means our N value is going to be 4. So the first thing we're going to do is we're going to write the function. Then we're going to figure out what the balance would be after 6 years. But first, let's talk about the function itself. So for the function itself, we're going to go into this template. You have it above, but just so you know where all of these values are coming from, right there. So for our scenario here, it would be Y equals, our principal would be $3,000. That's what you're starting with. 1 plus, and then this, instead of just being the decimal like it was a minute ago, we're going to write that decimal, but we're going to divide it. So we're going to write the rate as a decimal, but we'll divide it by N, which is how many times it's compounded. And then in our power, we're going to have N times T. Well, T is still going to be our input or our dependent variable, but if N is 4, then it's going to look like that. Okay, now I do want you to clean this growth factor up. Okay, so before you box your answer, go ahead and take that and clean it up a little bit. So maybe we'll come over here, we'll find out what is 4% divided by 4, and then add a 1 to that. So really, our real base here, our growth factor is going to be 1.01. Okay, so I just divided this and added 1 and cleaned it up. So this is a nice cleaner version of the same problem. And up here, it's going to be a 4t. That would be the first part of this, which is coming up with the compound interest equation that models this situation. There's that. And then now that we have that, we can sort of go for part B here, which is to solve for when time is 6 years. They want to know how much we have. What is our balance after 6 years? So now we can just use that input into our function. So it's going to be, we started with 3,000, we're increasing at this rate, and then when I put in that 6 up here, it really means a power of 24, right? So I'm doing 4 times 6 up here, which is going to be an exponent of 24 up there. Okay? That's what I'm going to put in the calculator, and then we'll find out what that is approximately. So let's grab our calculator. So we're going to do it with 3,000. This is our growth factor. And we're going to raise that to the 24th power. So after 6 years, you're looking at about $3,809. You have an increase of $809 there for a total balance of $3,809. That's a 0. And 20 cents. Let's go to the money here. Yeah, that looks good. Okay, so about $3,809.20. That would be how much we would have in that account after 6 years if we were good and didn't touch it. Okay, all right, let's try one more, and then we can check the other ones when we get to class. So here you have a $5,000 deposit that earns 1.2% annual interest, and this one is compounded monthly. So again, this is our principal right here. Here's our R. We're going to change that to a decimal, and if it's compounded monthly, that means n is going to be 12. So once again, let's start by writing our function. Okay, so y equals p1 plus r over n to the nt. And let's fill in what we know. We're starting with a $500 deposit, and then we're going to do 1 plus our percent, but we're going to change that to a decimal, so it's going to look like 0.012. And we're going to divide that by the number, how often it's compounded, which in this case is 12. And then our power over here is going to be nt, but 12 is going to replace that n. And like I said, then I do want you to clean up this growth factor before you box this and give me the final function. So let's find out what that is. So I took my 12%, I changed it to a decimal. Then I took that decimal and I divided it by n, which is 12, and then I added that to 1. Interesting, same one. Not necessarily, did I do that right? Make sure I did. So is it 12% or 1.2? Oh, look at me. I almost did that wrong. Okay, so 1.2 divided by 100 makes it a decimal. We take that decimal and we divide it by 12, and then we add 1. That looks better. Okay, so it's 1.001 this time. We have an initial deposit of 500. This is going to be our growth factor right here, and that's to the 12t. This is our function for our compounded interest scenario. And then once we know that, it says what would be the final balance after 4 years. That means we're going to insert a 4 for t here. So we're going to solve this. Solve for when t is equal to 4. So that's going to change our equation to 500, 1.001 raised to the, when I plug in a 4 there, 4 times 12 is going to be 48. So that's a new exponent. Let's see how much money we'd have if we left that alone. So $500 times 1.001 to the 48th power, we'd have about $524.57. Okay, so that would be our balance there. And like I said, try the next two, and then you can check them Use this as your template and as your guide. Try them out and then check them to see. All right, check to see how you did on these last two exponential or compounded interest formulas. When you had the $48,000 at 6.3% semi-annually, this should have been your function. And then evaluating that for what your balance is after 10 years should be $89,253.63. That is an excellent return on your money if you can hang in there those 10 years. This one here is a little more complicated. This decimal comes out so small that I actually, when I used the calculator, I left it exact like this, even though here I estimated what it was, simplifying it. But in the calculator, I left it like this as I entered it when I solved over there. But this should be your function. You're starting off with a $1,275. You're doing 1 plus your interest rate as a decimal divided by the number of times you're compounding. That's where you get this lovely thing. And then you're raising that to 365t. And then if you want to evaluate that for 9, you change your exponent to 365 times 9. And you evaluate that, and you'd have $1,280.75. Those are very low interest rates, so it makes sense you didn't make a whole lot on that investment, but you did make some money. All right, so hopefully those went well. We'll discuss these in class if you have any questions, and then tomorrow we'll do exponential decay.